Thank you very much for the invitation to the conference. I'm actually very glad to be in Weizmann Institute. I essentially first time here. And I'm very glad to be on the conference dedicated to Joseph's 72nd birthday. And I have a little comment about this. Actually, can you put some light? So, huh? They're working this. So the comment is the following. So there's a Hebrew word. So if I can make it. So in English, it's you write it high. And in English, it means live. Now, why it's here? Because the gematria, the value of this, numerical value of this letter is 10, and this 8. 10 plus 8 equals 18. And now we notice that 72 is 18 times 4. So I guess this is the reason we celebrate 72nd birthday. And so I can just wish to Joseph a happy and productive next 18 years, and hope very much that we'll celebrate 90th birthday, which is 5 times 18. And I hope to be around and to be able to say something on this occasion. And maybe before that, but definitely for the high. Because if you don't quite know the Jewish tradition, so if you wanted to give a gift to somebody, like something, money, for example, donate, you're supposed to do this in multiples, integral multiples of high. So that's what we do here, 4 times high. All right, so so now let me start the talk. So let me start with a little motivation. So in arithmetic algebraic geometry, if you have variety x over q, then there are 2 ways you can treat this variety. So you can treat it in Gullah theory. I mean, using the Gullah theory. And so what you do, you consider a topological homology of this variety, SQ bar over Q, with algebraic coefficients. Or you can do analysis, so let's say Hodge, and then you do something different. You take the set of complex points of this variety, and you consider n-dimensional cohomology, let's say with real coefficients. And then 2 things happening. So first of all, here on the right, we know that this is an R mixed Hodge structure. And here we know that the Gullah group of Q bar over Q acts on algebraic cohomology. Now, if you assume for a second that X is actually smooth and projective, then we can say more. We can say that if you have point P of good reduction, then there is a Frobenius element acting. And then this Frobenius element has eigenvalues. And their absolute value is P to n over 2. This is a famous Wales conjecture proved by Deligne. And here, actually, the result goes, well, before that, this theorem of Hodge, which says that if you take this Betti cohomology, you can call this Hn Betti, tensor C, then this is direct sum of HPQ. There's a PQ decomposition where what's important is that P plus Q equals to N.
It's a different P.
What? Sorry, I didn't understand the comment. So there is a Hodge decomposition, and so the N is the same here. And actually, it's quite mysterious, so why it appears, why it works this way. So, but now we understand that it's not just that these things two are analogous to each other. We really have to consider them together. So for each prime P and for infinity, prime at infinity, we have to put them together. Why? Because, for example, if you want to make something like L function of X, S, then you better make a completed L function, so which is the usual one, which is defined using the left-hand side, and you put the Archimedean factor. And the important point is that you really need only real Hodge structure to define the gamma constant, the gamma factors. You don't need the rational Hodge structure, you need the real one. So this brings us to the following list of analogies, which is very well known. Where is the razors? Let me just erase this because Blackboard is not too big. So the list is the following. So on one hand side, we have Gullah Q bar over Q models. And they form a category. And on the Hodge side, we have the category of R mixed Hodge structures. And so this category is equivalent to the canonical equivalent to the category representations of some real Hodge algebraic group. And so you can deduce from this the main conclusion. The main conclusion is that this Hodge-Galois group, G Hodge R, is the Archimedean analog of a decomposition group at P, which is defined up to conjugation and sits in Galois group Q bar over Q. Now, I want to stress that I consider, and this is an important point, that I consider the category of real mixed Hodge structures. That's why I was talking about L functions, and not rational mixed Hodge structures. There's a finer invariant, which is rational Hodge structures, and it is irrelevant to the story I'm going to talk about. It's kind of leads to different worlds. So, talking about this one, it has the following structure. So this Hodge-Galois group, it is projected to the real group GM C to R, and the kernel of this canonical map is a unipotent radical. So we're going to remember this. And so this is the analog of the inertia group in the decomposition group. Okay, now more to this analogy, that there is a reason. So the very fact that the Gullah group acts on cohomology, étale cohomology, is just a linearization of a geometric fact that actually GQ acts on étale side. Let's say Fx. And therefore, it acts on the category of étale sheaves. And therefore, now you linearize, it acts on the étale cohomology, or X group between the sheaves. Now, this is how the action of the Galois group is constructed, but if you look at the right-hand side, there is nothing like that. So there is a kind of big question mark here. So what is the analog of this? And so we don't quite know what's the analog of this. And so somehow we're missing, the main point is that we're missing a huge piece of geometric information. So we miss all this thing. We just see the action of the Hodge group on the cohomology, which means we see the mixed Hodge structure. And the way it's defined, it's not resembling in any way the way the Galois action is defined on étale cohomology, because here it comes from symmetries, and here it does not. So the upshot is there is some kind of hidden Hodge symmetries which we don't see yet. Now, I just wanted to remind that the way things were developed, that the analysis was first. So first of all, we had Hodge theory, and then the ladix theory was developed. And so now here, it's kind of going backwards, so we don't quite know what to put here. And so I have some proposal to this. So the proposal is the following one. That's a proposal. That's what I'm going to talk today. That let's suppose that we have situation of a base. Let's suppose that we have a map which I'll assume, let's say, proper map of complex varieties over C. Then one should have some structure, extra structure. So you can call it open string theory structure on the category of holonomic D-models. All holonomic D-models, not with regular singularities, all of them with irregular singularities. So this is, if you consider with regular singularities, this would be perverse sheaves in topological settings. But let's consider all of them. So there should be some data. Now, what is this data? And so the proposal is that it's given, I will explain what I mean by this. It's given by what I put as the title, this quantum Hodge field theory. Now, after this introduction, so let me actually explain what the structure of this, what the structure is, quantum Hodge open string theory structure. Oh. So this quantum Hodge field theory is given by something which I called quantum Hodge correlators. Some like of correlation functions of something. And so what is the structure of this quantum Hodge correlators? So first of all, to explain the structure, I can talk about more general setup. So let's suppose that we have a semi-simple Calabi-Yau to n, it's even number category, which means the following, that first of all, this category has homes which I suppose graded vector spaces, not even complexes, and finite dimensional in some sense. And most importantly, there is a pairing Pxy from home from x to y, tensor home to y to x, into some dualizing object H, which has degree 2n. This is because it's Calabi-Yau 2n category. And it itself is invertible object in some underlying category. So, for example, vector spaces or something you deal with. And so this is functorial perfect pairing. So that's the notion of Calabi-Yau category.
So AXY is home XY?
Yes, yes, yes. So A dot XY means home in this category from X to Y. Dot means that it's a graded vector space, as I said. Because I have to have grading because my main object, H, is in degree 2n. It's graded. It's very important.
Graded by what?
What?
Graded by what?
By integers. So now today, I will consider a specific example of this. So I will consider Calabi-Yau 2n category, which I denote har x over b, category of harmonic bundles. Remember that we start with a relative situation over the base, and its objects, in spite of the word harmonic, the objects are entirely topological, so this is just semi-simple local systems. Semi-simple complex local systems. Maybe the shifts on X. Now homes. So if you have two local systems, L1 and L2, then you define home between them, which is what? So what you do, you take internal home from L1 to L2, or L1 star tensor L2. So this is a local system on X. Then you can apply a case direct image to the base. So this P is a projection to the base. And of course take sum over all K. So you get a collection of local systems. I assume that the map is smooth, so no singularities. So you get direct sum of local systems sitting in degree K, each on the base. Now, who is the dualizing object H? This is just a relative fundamental class. So direct image on the constant sheaf. Okay, so this is my category. But if I have any category, Calabi-Yau category, yeah, what?
Can you just read what you wrote? So objects are what?
Objects are semi-simple local, complex local systems on X. or maybe the shifts. X is a smooth, let's say, smooth projective variety over complex numbers. Huh? Yes, it's a relative situation. So you have local systems on X, but when I define Holmes, I'm not going to get a vector space. I'm going to get local system on B.
Okay, so you have morphism X. So
Yes, you have morphism X to B. That's the input.
it's on as
Huh?
it's on as so,
Yes.
okay, so
Yes.
that is this stage.
Yes, yes, yes. This is my category enriched over local systems over on B.
Do you think that this smooth morphism?
Yes, yes. It is as nice as you wanted. It's a smooth morphism of complex projective varieties. Because I don't want to get to D modes. Don't want to get any singularities. Okay. Now, starting from this, from any Calabi-Yau category, we can define the main algebraic object which governs the game, which is some DG Lie algebra. So let me define it. So if I start with any Calabi-Yau A, I'm going to define certain DG Lie algebra, which I will denote Lie of my category A. And I need some technical notation. I need to introduce dual space to the home group. So this is just A dot downstairs. You take home in this category and dualize it, like homology. And now the other input is a decorated surface. So given a decorated surface, so it's an open string series. This means it depends on some topological data. So it's decorated surface S, which is by definition an oriented topological, of course, 2D surface with boundary and some extra data, which I call special points on the boundary. Huh? I mean surface. Just emphasizing it's not algebraic surface, it's surface. Special points modular isotopy, special points on the boundary of the surface. Now, the best thing to do is draw a picture. So what you have a picture like that. So you have your surface, this is my S. And on this surface, you have special points. So I'll write them by red. So here we have one special point, and here we have no special points. That's also okay. And now the data which I want to associate to this, I want to have a notion of A decoration of S. A is my category. And let me give you the simplest possible example of a decoration. So let's suppose that your surface is a disk which has 3 points here. Then how I decorate it, so I put objects of my category on the interval. So here I put x1, x2, and x3. And then as I have also homology, like dual to X groups between them, which I denote by these red arrows. So they are attached to special points. And so this one, for example, is a lower dot from x1 to x2 shifted by -1, and so on. Now, if you have more complicated surface, you have more decorations like you have here. Wrong color.
When you say so on about this -1, it's -1 for all of them, or?
No, -1 for this particular home. You take this home and you shift it by -1. You shift it to the right by 1.
So what happened to the others?
Everywhere, here and here, I shift by -1, by 1, yes. In homological algebra, that's what you always do. Whenever you see something, you shift it by 1, and then you start doing something. So now you put here some objects like x, y, and z, and then you put like t, and then you put, I don't know, p. So you put objects everywhere, but the homes just put arrows here. You put here, you have just endomorphism of this object, and here you have nothing, no red data, just an object. Okay, so this is the input. Now, what do you do with this input? So I define this some space which will have DG Lie algebra structure. So let me define this space.
Sasha, when you write something red, is it a vector space or an element of a vector space?
Red is not a vector space, is a local system. I mean, in this case, it's a home. Let's assume that we call that the home, the dual to home is the greatest vector space. Let's just settle for this, okay? But later on, it's going to be in our main example, local system on B. Actually, direct sum of local systems shifted by.
So here, in this example, B is a point?
This is abstract example. There is neither X nor B. This is abstract Calabi-Yau category. There is no geometry.
But you take it enhanced over something so that these are objects somewhere?
Let's not go that much into discussion. It's definitely enhanced on something, on some semi-simple tensor category. So in the example, it will be tensor category of local systems on B. But let's just say this is a vector space, it's just for simplicity of the language. Okay.
Sash, what is n for this abstract Calabi-Yau
What?
category? What is n, the degree?
2n, it's 2n Calabi-Yau category.
And where is n in this
Integer, it's an even number. Not odd, but even numbers, that's it. Yeah, it's just even number. We have no geometry, no x, no b, just even number, okay? Where it is here, the dualizing object h sits in degree 2n. That's how we remember about this.
But can we see n
No,
anywhere else?
no. We cannot see n anywhere else. It's just that's it, okay? So it's just the formal data. So let me remind you that we have a special point, P. Ilya, you still have questions? So? Then maybe we discuss a little later, because it's a formal situation. It's any Calabi-Yau category dimension 2n. All right. So to any special point, as you see on this picture, we assigned what? So we assigned because we have decorated surface. I write it again. It's home from object xp minus to object xp plus. So here I introduce a notation. So if you have here some point P, then here we have object xp minus and here xp plus. It's the left to P and right to P object. And so we put just home between them. Okay? Now we make a definition. It's some generalization of cyclic homology of the category. So we take C dot related to the surface S and the category A to be direct sum over all A decorations of some particular decorated surface S. Now, then for each decoration, you have tensor product over all special points of these home groups assigned to them, which I just introduced. Now, then, since you want to have something assigned to a surface, you're bound to take co-invariants under the mapping class group of S. And so now that's the object. And so by definition, the Lie algebra is not yet the Lie algebra. The Lie algebra of A is defined as a direct sum over all isomorphism classes of S of these huge guys with certain corrections. So you have to tensor by some power of the fundamental line in the Euler characteristic of S, and to something else which is extremely important, there's some orientation torsor related to S, and shift by -1 to the right. So this is the guy which is going to have the structure of the Lie algebra. Okay, now I almost defined it, except that I didn't tell you what is OR S. And this is very important. So let me define what is OR S. And as you will see, it's the meaning of OR S is the following. This is just the space of volume forms on a certain moduli space, some kind of a moduli space related to my decorated surface S. But I wanted to do this in a very formal way. So I'll give you just formal definition which follows from the idea which I just said. Formal definition is this. Let's take gamma, which is S3 valent, ribbon graph with a set of legs, which I call L1 and so on Lk, and the set of edges, which I call E1 and so on Em. So any graph has legs and edges, trivial graph. Now I define the orientation torsor of the graph. And this is by definition the following z-line. So I introduced some formal object EI, which has degree +1 and corresponds to HEI, and some other formal variable LJ, which has degree -1 and corresponds to the leg. And so now I take just element of the corresponding determinant. I just write in this way, which L1 and so on L I call K. And so this is just isomorphic to Z sitting in degree K minus M. As I said, it looks a little mysterious. It will be more clear when I give the main construction. And also you can consider this as just a computation of some natural torsor which sits on some modular space which I didn't define for you. But the main point about this is the following. That first of all, as everybody knows, if you have a ribbon graph, then it produces you a decorated surface as gamma. So for example, if you have Mercedes sign, then what you draw here, you draw a disk and it has 3 marked points because you kind of assume that you make it like that. So you have, and so on. So you get decorated surface. Now the legs of this graph become the special points on this decorated surface. And now there is a claim, which would be less mysterious if I use a definition with the volume forms, that if you have 2 surfaces which are actually isomorphic related to 2 different graphs, then the corresponding orientation torsors are related by some isomorphism. So I wrote equal, but all this means that I can consider now any trivial n graph which gives the surface, take the orientation torsor of it, and declare it to be the orientation torsor of my surface. So I basically say that it follows from this that there exists this torsor I'm talking about, and it can be understood as the orientation torsor of any trivial n graph related to this picture. Again, what really is going on is that this modular space has the compositional cells which corresponds to stable differentials, and each graph gives you a cell. The cell is oriented, has canonical volume form, and that's how they all fit together. But we're just doing this formally. Now the main point is that now you have the after this this DGLE, this vector space has a structure of DGLE algebra, and it comes.
Can I ask some questions?
Go ahead.
Yeah. So first, just to understand, I'm far behind. So the indexing for your Hans. So if we have the example of X mapping to B.
No, we don't yet have this example. It's irrelevant.
But you told us this example, and I just want to understand how.
Not yet.
things work in this
Not
case.
yet. I forgot about this example.
I didn't forget about it.
That's not good. Please forget. So it's irrelevant. It's a formal story. We don't want to do this.
I understand it's a formal story, but well, you're dualizing with the Columbia, and I can't do the indexing in my head. So can you just tell me, so if B is a point?
I'm not doing this. I have Calabi-Yau category. That's it. So I don't want to consider example. Be with me a little bit, okay?
Did you define
Okay.
Calabi-Yau category?
Yes. So in the, okay, fine. So in your construction, so the definition of a decoration involves some kind of degree 1 map. And I don't see it appearing in this definition of six.
I don't have degree 1 map. I just have the pairing, and I'm going to write this pairing. So intersection.
No, when you wrote down the definition of a decoration, you put an object at each point, and then you put, sorry, an object on each interval.
And then I put just homology groups. Okay, if you want to have, listen. So
this was exactly the question I was asked. You were putting down a morphism
yes.
on the.
Yes. So let's suppose that we're really talking about one object that's constant shift. Then I just put homology of the variety X
I
shifted
forgot
by
about
1.
that example.
Good.
No, so it's the definition.
It's really not clear. So
Yeah.
first of all, what you said was confusing. So do you decorate with objects, or do you also decorate with elements of the concept?
No. The surface is decorated by objects.
Okay,
That's it.
That was the first question, yeah.
yeah, that was the question. Okay, so can I also ask something? So most of us are used to think of TQFT attached to a Calabi-Yau category. So yeah, so you have a decorated surface, normally attached to it an object of the tensor product of, well, the tensor power of your category numbered by the points. How is that object related to your
Sorry, actually means, so you can assume first of all that your category consists of one object. Then you're just talking about the group of endomorphisms of this object. This is your algebra. So you attach dual to this algebra to the special points.
Yes.
That's it. So what's your question then?
My question is, what is C in terms of TQFT?
Sorry, who is C?
CSA must have a meaning in terms of the TQFT.
I don't know. I mean, it's a definition. So
No. This TQFT has a definition independently of this. I mean, I'm asking, how is that expressed in terms of that TQFT?
Denis, I don't know. So for example, if you take the disk as your decorated surfaces, then this guy, this Lie, attached to the disk is what I call Lie classical, attached to this category. And this is nothing else but cyclic homology complex of your category, tensor fundamental class, and shifted by 2. So it basically cyclic homology complex. Is that good enough?
I don't see why it's in the algebra.
I'm going to tell you.
And Sash, what is H capital in this formula for
H capital is a dualizing object. Okay, so now let me tell you what the Lie algebra is.
Logic object was on V, defined on V.
Yeah, there is no B and X. It's a formal setting.
Yes.
Huh?
It's my question. So logic object, which one?
It's a definition of what is Calabi-Yau category. So there exists an object such that you have pairing of Holmes to this object. If you dualize it because it's a perfect pairing, you have a map to the inverse of this dualizing object. So I call this intersection pairing. Okay? Now I'm answering Denis' question. So how we define? We want to define something which I call the gluon map. So we define gluon map. And this gluon map will produce all the data. So first of all, we have
H, is it an element of some category?
H. Let's settle that H is a line. My category, let's settle for that. It's just the category over vector spaces. The Holmes are graded vector spaces. H is a line, one-dimensional vector space, which sits in degree 2n. Okay? Yeah. So now let's take two surfaces, one and the other. And let's try to glue them. So how we glue? So remember the surfaces are decorated. So let's say this is decorated by X and Y. Let's assume this is just simple objects in my category. And let's assume that the other surface is decorated exactly by the same objects. Or you can say by isomorphic, doesn't make any difference if you think about this. And then there are Holmes, which follow the orientation of the boundary. So this way and that way. Now, over this Holm is decorated by this guy shifted by 1, and this Holm is decorated by this guy shifted by 1. Therefore, it makes sense to glue them. So we glue, and so what we get after gluing, we get a new surface where we glue these two guys, so it's now punctured lines glued. Now, these 2 points are glued to some point there, but remember that we thought about the surfaces we used just for our mental, as a mental tool, the graph embedded there. And just want to trace what happens with this graph. So when you glue these two surfaces, the corresponding graphs also glue, but what happens is that you get some extra internal edge, and the two legs, which you have seen, they are gone. So that's the difference. So you glue two things, okay? Now, after you glue this, and after you apply the intersection pairing, you have to tensor to H minus 1, and in my definition, I tensor by this E related to this HE. So this is my definition of the gluon map. Is that clear now, Denis? Too fast, okay. So let's slow down. So what I'm doing, I'm taking two surfaces. Or maybe I take in one surface. Let's say I take in two surfaces, and I want to glue them in all possible ways. So first of all, my surfaces are decorated surfaces. This means that on every boundary segment, I have objects. Now, I allow to glue two special points if and only if the corresponding decorated objects are isomorphic. I just identify them. If they're isomorphic, I glue them, then the objects disappear. But what appears that I also have to kill the corresponding homes between them. And so I kill them by applying the intersection pairing. After that, I have to put this factor here. So I get a glued surface, which has an extra HE, and this factor, and then by my hands, I put here an extra element of the orientation torsor. Remember that when I was defining my Lie A, it has many copies of H to some power, and has this orientation torsors. And this allows me to glue and to get some map which has degree +1. Why it has degree +1? If you think about this, just because of this element, it has degree +1. That's it. So I define the gluing map. Yes?
Can you put another point on top of this red point? Because it's not clear what happens, how X disappears. Can you have another point on top of?
No, I don't have to. I mean, you have two objects here, X and Y, and you have two X and Y.
You have another object on the left of X.
Oh, sure, I can put this, something like that if you want.
There is an object Z there, so what happens with Z?
I mean, if you think about this, you'll see, so it's a good...
If I don't know the definition, what you said is not a definition.
It is a definition. So just look at this picture. Yeah, you're right. You're right. So I have here object like I said Z1, and here I have object Z2. So these 2 points, which you insist that I put, it's a very good idea. You see it here and here. Because when I glue, these 2 points are gone, but these two give me... So I glue this guy and this guy. So these 2 points remain. Okay? But what is on the left, you see here at Z1, and what's on the right, you see here at Z2. Is that clear now? All right. So I define the gluing map. Now, this gluing map produces everything. First of all, you wanted to have a Lie bracket. So if you want to have a Lie bracket, so let's call this this guy. Then what you do, you glue points, special points, on two decorated surfaces, S1 and S2. But what you can do, you can consider just a single decorated surface, and still you can glue points. So this gives you another guy, which is a differential. So differential delta is what you do. You glue S, glue special points on S. So then you get, again, some surface. Maybe, like example, you have a disk, and when you glue 2 points, you're going to have some bridge here. And so you already have non-trivial topology, not a disk topology. So differential brings you, it makes topology more complicated. Here you just glue 2 surfaces. When you glue 2 disks, this is Tudini's question, you still get a disk. Okay? This is the Lie structure on the cyclic homology complex.
So, Sasha, are you summing over all the ways to glue?
Yes. I'm summing all possible ways to glue and all decorations. Yes, it's assumed. Is it okay? So this is a Lie structure on the cyclic homology complex. What's really important is that you have to twist this by H, because otherwise there is none. Okay. But also there is a third thing here. There is another differential, which called little delta, which comes as a Lie bracket with a distinguished object, which comes from the fact that you have a category. So far I didn't use a category structure. I just use the fact that I have pairing. I have just a quiver. Now I have differential D. It's given by the... So there is this kind of element which corresponds to triangle called nabla. And you take commutator with something. This is my D. Now what this guy is, so you have disk with 3 points. There is some canonical object. You have object like X, Y, Z. You have homes here. You take a sum. You have some objects which comes from composition of homes. You take X, X, Y, tensor A, Y, Z, and it goes to A, X, Z. So if you dualize this, you will see that you'll get canonical element assigned to the disk. And this gives me the differential. So now I have two differentials I commute and Lie bracket. So I get dg Lie. Okay? Yeah.
So Lie bracket is just delivering two surfaces in all possible ways. So what differential delta?
It's just a Lie bracket with one particular element of my.
Small. This is small delta.
Yeah, big delta, you glue two special points on the same surface. Okay. Now there's a statement. That's a claim which explains what is going to happen. I don't think it's going to happen now, but it was planned to happen. That if you consider H0 delta of this classical Lie algebra, the one which corresponds to disks assigned to A, this is just identified, it's isomorphic to Lie algebra of A infinity derivations of Calabi-Yau to n category A modulo homotopy. It's homotopy derivations. But a smarter object would be to take not the Lie algebra corresponding to the disks, but the big one. So now you take Lie algebra corresponding to A, and now you take its H0 in delta plus delta with respect to this differential, and it maps naturally here by forgetting all surfaces of complicated topology, just leaving disks. And on the other hand, it can be served as a definition of quantum A infinity derivations of Calabi-Yau to n category A, modulo homotopy. Okay? Now, you should probably ask me a question why this is true, because this is a statement that whenever you have some cycle in this Lie algebra corresponding to disk, it produces you A infinity derivation. This is actually clear because what's derivation? What's A infinity derivation? It just can be understood. You take the bar complex, you dualize, and then you have a derivation of that. So how you make it? So if you have something which lives on the disk, so this something it just flows to this chain, and whenever it sees, like you have say object like x and y, whenever it sees something which is similar here, you just kind of glue it together, and then you get something which looks like that. So you get a new chain. So that's how the Lie algebra acts by infinity derivations. So that's a construction. Okay? So now the main statement. So the main statement is that the Hodge-Gullah group. Now we return to the question, to the example which we studied before. So this is going to be main result when the base is a point. So now you have to remember that I have a map from X to B. And now in this case, B is a point. And so the theorem is that there exists canonical Lie algebra map from where? So you take the Lie algebra of the Hodge-Gullah group. Now, surely you forgot, so I remind you that we have this Hodge-Gullah group. And this Hodge-Gullah group has a unipotent piece, which is I called U-Hod. And so you take this Lie algebra. So the claim is that there is a canonical map of this Lie algebra to the one on the bottom. So Lie algebra with respect of H0 of this Lie A. Lie not A, but now this is this harmonic category I was talking about. Okay? Now I call this map quantum Hodge correlator. I need to construct it. But then, of course, since we have a projection, we can project down to H delta 0 of the same Lie Rx. And then we have a map here. So this is classical Hodge correlator. So the main result is that there exists a map of this Hodge-Gullah group, to be precise, unipotent part yet of the Hodge-Gullah group, to the Lie algebra, let's say here, of all A infinity derivations of Calabi-Yau category of harmonic bundles. Or in the quantum case, it gives you map of this Lie algebra to the Lie algebra of all quantum and infinity derivations of this category. Okay?
Things don't add up. So maybe I missed something in the definition. So your A seems to be just local systems on X. Right?
Yes.
So this is completely algebraic, not Hodge theory. I mean, it makes sense on algebraic close to characteristic zero. How come it has anything to do with Hodge theory?
I take a complex manifold and I construct a map from the Lie algebra of this complex manifold acting by infinity derivations of semi-simple local systems on the complex manifold. The construction is entirely transcendental.
Semi-simple.
Yes, semi-simple. It's a key, semi-simple, yes. I use classical Hodge theory, in this case, classical Hodge theory a la Simpson in order to talk about Hodge theory of semi-simple local systems. Here it's a crucial they're semi-simple. And then it's a very transcendental construction, as you will see, or you might see, which gives you this map. Okay? So, since you asked this question, there's another guy which appears here. So if you take this GM C over R, it also acts here because it acts actually on the category. Because this is a Simpson action. I don't define this, I'm just talking to people who know this. So Simpson defined actually Simpson defined something smaller. So let me settle for, he defined the action of C star. There's action C star on all local systems, and so in particular it acts on everything, so it acts here. And so the claim is that they actually agree that you get action of semi-direct product of this and this compatible, that this action is compatible with Simpson action. So this is just enlargement of Simpson action to the unipotent tail. So Simpson action is like the action of Frobenius in the unrefined situation, and this adding ramification. Okay? Now let me define this action. So before I define this, let me explain what I need to do in order to define this action. So the question it's a standard thing that it's a free Lie algebra with certain generators GPQ, where P and Q are integers big or equal to 1, divided by the only relation, the reality condition, the GPQ bar is minus GQP. The important statement here that this is not some isomorphism, this is canonical isomorphism. So the claim is that there exists some canonical isomorphism, which is already a very non-trivial statement that it does exist, and in particular works well in families. So there exists canonical isomorphism. So usually Lie algebras which are free, they don't come with generators. This one does. And I'm going to use this. And so now in order to construct a map, if I wanted to construct a map from basically free Lie algebra to somewhere, I just need to tell you where the generators goes. And so I can just dualize this. And so all I need to do is define a map which I really call the Hodge correlator map, which tells you, which takes this H0 of this Lie algebra, Lie harmonic X, and maps it just polynomials in two variables, Z and W. Why is that? Because these GPQs, you can just make a generating function out of them. Z to P, W to Q. And so instead of defining these maps component-wise, you can just define all of them. And so this means that you need to produce some map to polynomials in two variables. These two variables, they are coordinates on a certain plane, which I call twistor plane. This is one of the explanations why twistors appear here. Okay, so now let's do the construction. So I'm going to construct this map now. But let's just think, what do we need to do? So we need, I need to dualize this. So what I need to do, I need to take the created surface, colored by all those objects, actual dual space to this, and I need to assign to the decorated surface over the base something, but over point just a number, basically. And so this is this Hodge correlator construction. So now it's the main point of the lecture. So let's do this. So it's construction of quantum Hodge correlators. So first of all, we start with the data. So the data is the following. You have gamma, which is a 3-valent ribbon graph with legs. I'm just saying this for completeness. And no simple loops. That's essential. So you think about this as a picture like that. So you have ribbon graph. This is a planar case. And to each phase f of gamma, you assign some object of your category, L sub f, which is object in this category of harmonic bundles on X over B. So for example, you put here object L1, L2, L3, L4, L5, L6. Now, this data allows you put more gadgets related to this. So let me list them. So first of all, if you take a flag f of gamma, and the picture is the following one. So you have, let me draw just an edge for simplicity. You have an edge, and now you have a flag. This is my flag f. Now, if you draw this flag, then there is some object to the left, let's call it f, and some object to the right, let's call it g. There is face to the left, face to the right. And so we assign to this flag some object LF, which is just home from one to the other. Remember that we have here some object, and here some object. They just home from this object to this object. Okay. Now the most important thing, which I actually don't have time to properly explain, it's somehow one of the main points, that if you have an HE of gamma, then you assign to this propagator. Whatever it means, it's just which is a green current. And this green current, by definition, is a certain distribution which is specifically constructed and has some standard properties, but some specifically constructed green current, which lives in 2n-2 distributions on x cross x over b with coefficients where. So you think about this form. This is distribution lives on some copy of x attached to this vertex and some copy of x attached to that vertex. This is my x over b. Okay? Okay.
Can you just say one more time? So you're trying to construct a certain map between two vector spaces. Both have a basis, basically, right?
No. Where do you see vector spaces?
Well, one is H0.
What?
One is
Oh, you mean this one? Yes, definitely. Yes, very good. You want to construct a map between linear vector spaces, and they come with bases.
Yeah. So it's basically the basis here, you want to attach a number.
Yes.
So what are the parameters? I mean, again, you want to attach a number to what kind of data?
So the data is exactly what you see here. So you start. It's a very good question, Denise. So it gives me a chance to introduce again. So you start with a decorated surface. So this is your gadget. It's a decorated surface. Okay? But now you assign to this decorated surface, you take the dual to that. So the gadget is that now I put it like blue. So this homes, it's actually a upper dot xy shifted by 1. But basically it's just x group between the objects. So you take a surface, put the objects there, put x group between them. Now I want to get a number, or over base, I want to get a differential form out of this. Okay?
On X.
On B.
On B. Okay.
Yes. First of all, I will get it on x, correct? Then I will integrate it down. It will not be on x, it will be on x to some power, but then I will integrate it down, we'll get it on B. Okay? So you're right, my goal is to construct differential form, but where on x over B raised to the power given by the vertices of some graph gamma, which is somehow trivial graph built in this surface. So I'm going to insert one of the many trivalent graphs which you can put here, and for each of them I'm going to construct differential form here on this relative tensor product over all vertices. So my copies of X live over the vertices of this trivalent graph. And so when I was saying my data is trivalent graph, I keep this as a kind of secret that this gamma is going to produce me in the end of the day as gamma. And so that's where the data actually lives. Okay? Good. But I can rephrase the same data on gamma, and that's what I was doing before. So this data decoration is exactly what you will get after you construct the corresponding surface. Okay? Now, the main point is that I need to construct some green current, which is something which lives on X cross X. And these two copies of X are assigned to these vertices. And it's technicality, so it lives in the tensor product of two local systems, this LF star, tensor P, G, L, G. Who is F and G? So here you have when you have H, you have flag F and flag G, okay? And so you have projection to the F, to the copy of X which sits here and copy of X which sits here. This is my projections. So you take this guy, which sits over this edge, and you pull it here, and take this guy, which lives over this flag, and you put it here. Okay? Okay? All right. So you like control listeners. So if you say that it's okay, and somebody asks me a question, you are going to answer, not me. All right? So you put here distribution. Now, I need to give you construction after all. So if you have a leg L of gamma, then you assign to this some kind of similar data. So what does mean leg? So you have some leg L, and you have some object, which let's say F on the left and G on the right. And so you assign to this what I call Casimir element. Let's call it C sub L, which lives in it is a harmonic representative of a certain cohomology class, which lives in the cohomology of this LF star tensor LG, tensor dual space LF LG. So what happens, this harmonic represents is they represent cohomology X group between LF and LG. And so I take a tensor product of a X group and the dual of X group, and there is identity element there, there's canonical element there, but I represent it by harmonic forms because I didn't tell you, but I have Hodge theory, so I have harmonic representatives, that's what I put here, okay? Now I all set, last piece of data is that I have a trace map, which is a map from tensor product of these LFs sitting over flags attached to some vertex V to the constant local system on B. But now I can all set, and I can just say what the construction is. So that's the main point of the lecture.
What's the upper index in G means G to N minus 1?
Yeah, that's it. What?
Upper index, red G.
Oh, this is distributions of degree 2n minus 2.
What do you mean degree?
Differential 2n minus 2 form with singularities.
Like forms.
Yes, it's forms, but with singularities. Yes. So now we take a twistor plane. I write it again. This is plane C2. Just has canonical coordinates Z and W. And then we do the following. So we start with the graph gamma. And then I'm going to attach to this graph gamma, as Denise was anticipating, differential form kappa gamma, which is a form with singularities on the space X over B raised to vertices of gamma. Cross C2. That's very important, cross C2. But on the other hand, this space can be projected down because it's a fibered product just to B cross C2. So let's call this map pi. And so the main point is that this form is going to be current integrable form. So I would be able to take the push down of this form, and so I get another current kappa gamma. That's what I really want. And so this is a form, and now the theorem, this is a current. It's integrable singularities. This is the main technical theorem. And then this will be another current on this space. Now how I construct this form? So I need to introduce some funny differential operator. Now, for now, you can just think that all my local systems are just constant ones because I don't have time to tell you what to do in general, but it's possible. And so this is just W d prime minus Z d double prime plus Z dW minus W dZ. So this is just differential operator of first order, which depends on the twistor plane. And now I just do the main construction, so this form kappa gamma, by definition, is this. So first of all, you take this operator dc, and you apply this to the green current, which corresponds to the HE1, and don't forget to tensor with the elements of the orientation tensor E1. So all this is something which has degree 2n, because the green current has degree 2n minus 1, 2n minus 2, this is 2n minus 1, this is 2n. So it's odd even degree. It's crucial. No science problems. So here put dc G green current EM wedge EM. Then you put wedge product of these Casimir classes. And what you get in the end, you get some huge differential form which lives on this space, fibered copies of XB tensor cross C2 because Z and W floating around everywhere. But it's formed with values in some complicated local system. You get down to numbers just by taking product of traces over all vertices. Now this is just form, and the main theorem, theorem B, that this form is a current. Now I can just define what's the quantum Hodge correlator. It will be sum of this form. Okay. So now I assign it to a single plane trivalent tree set in differential form on B cross C2. But it's actually not quite a differential form, because if you think, let me just explain what you really do here. So let's say you start with some tree like that. So you put here some objects like local system L1, L2, and L3. So in this case, you have no edges, you have no green currents. So this term is gone. But you still has this Casimir classes, which give you something in homology group and something in cohomology group, some harmonic forms here. So what you do, you take trace of those forms and integrate, but after this, you have this external data. And so this external data is actually lives somewhere. So let me now make a definition which tells you where it lives in particular. So the quantum Hodge correlator class, let's call it just G. It's kind of high analog of green function, is given by a sum over all connected graphs gamma as before, weighted sum of these forms with values in local systems on B. And so precisely it's going to be distribution on B cross some form of degree at most 1 on C2 cross some element in this Lie algebra of harmonic forms on XB. So it's crucial that you get here differential form with values in this Lie algebra. And I hope it's clear why, because what happens that when you have a complicated graph, as usual, when you write a Feynman integral, so what you do, you have some propagators living here, you have some data living here, but then you integrate all this out. This is all gone after integration, but what remains is the external data. And the external data is, by my very definition, is going to live here. And so you get differential form with values in this external data, and that's what's written here. And I'm almost done. So now I can formulate a theorem, theorem C. To formulate it, let me remark the following, that this is dg Lie in the category of, local systems on B, okay? But in particular, it's a local system, so it has the corresponding local system connection, which I call dB. And so I consider what I call twistor connection. Nabla corresponds to this Hodge-correlator class, which is the connection on this guy here, plus the RAM differential on C2, plus differential in my Lie algebra, plus this form. This form turns out to have degree +1. So all this gives you a DG connection. So it's a twistor DG connection. And so the claim is that this delta DG square is flat when restricted to twistor line Z plus W equals to 1. And this turns out to be equivalent, I can explain if we have more time, to so-called quantum. This is a reformulation of quantum master equation on this G. Now, quantum master equation here, I'm now finishing. So what you need to do, this is just some gadget, but what you really get, you're sitting in R home in the category of mixed Hodge structures, R home 1, from R of 0 to this DG Lie algebra Lie of har xb. And so there's some kind of smart definition of this R home, which gives you not just cohomology, but DG Lie algebra on the level of complexes. And the claim is that you get some saying that this G produces actually some Maurer-Cartan element here. And so what this condition really means, that this delta G equals 1/2 GG. So you get Maurer-Cartan equation. So why, it's another story, but that's the meaning of this. That on this language I just produce some flat connection, but it really means that I produce some Maurer-Cartan element in some DG Lie algebra. Who is this DG Lie algebra? It's not this one. It's X group between R of 0. It's a Hodge cohomology of this DG Lie algebra. So in Hodge cohomology of this DG Lie algebra, which is just DG Lie algebra over point, so to speak, you produced just a cohomology class. This is a Hodge correlator. And the main claim that it satisfies Maurer-Cartan equation. And this over point, it's just a very mild condition, but it just gives you what I want. So this implies that I have this map. That's it.
Okay, are there any questions or clarification?
So just again, that was so fast I couldn't understand what belongs to what. So is it correct that what you were explaining in the middle blackboard was all about the construction of that slanted arrow?
Of what, sorry?
That arrow.
It was the arrow down.
The arrow down.
Yes.
Okay.
The construction was over arbitrary base, but over point, it is just constructing of the arrow down. Yes.
Okay. So just again, all of this completely new to me. So
Denis, you don't understand it, and it's clear. There is a reason for that, because I didn't quite explain why this gives you that. Let me just say a word and
I just a much more basic things. First
Okay.
of all, if the arrow that goes like this.
I don't understand. Like this means up.
Classical.
Yeah, the slanted arrow,
Yes.
this arrow. Is it something known before?
No.
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 Okay, so both are new.
Both new.
So, well, I can understand that arrow. I mean, it goes between more or less familiar objects. One is the Lie algebra of this unipotent group, and the other is, well, the Lie algebra of the category of this category.
This is the Lie algebra of A infinity derivations
Right.
of this.
So at least the two objects are known, and then
Yeah.
let's start.
Let me just interrupt. So I said no, but in some cases, yes. So for example, if you consider, for example, just variety of a point, then what you're talking about construction of a map of this Hodge-Lie algebra to the algebra of A infinity derivations of the cohomology of the complex projective manifold. This is just a reformulation of the fact that on a rational homotopy type, you have a mixed Hodge structure. It's equivalent.
Okay.
This is known.
So, okay. So when the base is the point, then it's okay. Then
No, the upper arrow, I mean, not that it's known in full generality, but at least in some cases, this is just a different, I mean, I said it's known, but it's a different construction. It's entirely different construction.
Great. So, but then at least the meaning is clear. What's the meaning of this arrow?
Good question. So it's a quantum deformation of Z.
So the object itself is completely new. This,
Yes. Yes.
why did we want that? Can
I don't know why we want it, so I'm saying that I have it. I can try to give you, I mean, if you're, I don't know, there's like lecture supposed to end, but if you're willing to listen, I can give you some answer what I think it means. So what I think it means is the following, that remember that in the... Huh?
You can tell me to privately because I'm not sure everybody wants.
Okay, let me just tell you one word. So I think it means the following, that we constructing here some kind of, so we have L-adic realization, we have Hodge realization. We see here some kind of shadow of quantum realization which interpolates between them. So that's what this quantum guy is. So why, I mean, I can explain why, but I actually know that. So all this indicates that we have some kind of notion of quantum periods and quantum motives and so on, and we see some trace of this here. So if we just work on classical level, we work with the classical stages.
Quantum means with higher genes.
Yes, yes. High genes, I mean, classical means disk. Quantum means, for example, sphere with punctures. It's already a quantum in this language. It's not high genus, but it's already different than the disk.
It's supposed to capture momentum information.
It captures some information, yes. Some new information. I don't know what it captures. Okay. I can give you actually a different answer to the question. So there's two answers to what this means. So I gave you a first answer. The second answer, I wanted to tell you, Enrich. So what's going on here? So we're constructing some kind of quantum Hodge field theory. But what this quantum Hodge field theory is doing? So there's a well-known analogy that if you take, for example, Riemann surface or complex manifold, take Riemann surface. Riemann surface from the point of view of Hodge theory is three-dimensional manifold. So these green functions we're talking about are like linking numbers on this three-dimensional manifold between the links which corresponds to the points. Now on three-dimensional manifold we have a Chern-Simons theory like Witten, Zinger, Axelrod, Kontsevich, and in a much more refined version Reshtikhin-Turaev, which tells us there are some quantum invariants. So what's going on here? We don't do Reshtikhin-Turaev stuff. We basically, this is similar to Kontsevich or Zinger Axelrod, a perturbative version of the Chern-Simons theory. It's literally similar. It cannot be deduced from that. It's similar. So if you take this analogy that complex varieties are similar to odd-dimensional real manifolds, on odd-dimensional real manifolds we have this Kontsevich or Zinger Axelrod story, or it's better to say you have Chern-Simons. And what we have here, we have this kind of complex Chern-Simons. We have different Chern-Simons story. But it is of the same flavor. So instead of green functions, which means linking numbers, we see more complicated invariants of links, which in this case is high green functions. So it is a perturbative series expansion of something, but this something actually becomes really interesting when you do it like Reshtikhin-Turaev style. Yes.